This is the only talk with the QR code. I like that.
Yeah, new generation of presentation.
Many compliments. You
I
like
know.
you like
QR code. You could have a QR code on your talk.
Something creative. Initial slides get a compliment from you. I don't know what yet.
Actually, in a lot of the ML venues, it's almost like everybody does it.
Yeah, I think that's why
That's all right. We're gonna go ahead and start the last talk of the day. I have the pleasure of introducing Beyazit. I'm a little biased, but I think this work is quite nice. No, so I've had the pleasure of working with Beyazit now for many years. I won't say how many for both of our sake, but this work I think really starts to straddle some of the neural symbolic reasoning and trying to make these formal structures something that these RL agents can really understand. And so I'm going to let Beyazit obviously handle the actual exposition, but it's a real pleasure to have him here today presenting. And yeah, I'll turn it over to you.
Thank you very much for the intro, Marcel. Yeah, this is a project that we've been working on for some time now. It actually started as a class project, and then things get revealed to us, and then we realize it's actually quite interesting. So let's get started. So I think we've been talking about this. I'll just quickly motivate that. We've been seeing these chat boxes or VLAs, these kind of multitask autonomous systems, and they seem to give us interesting results. And so how should we think about trustworthiness in this context? And specifically, we want a system capable of performing a large set of temporal tasks. And then the user queries a task at runtime, but the agent doesn't know this a priori. So task can look like, deliver this box to the living room while avoiding passing by the bathroom or something like that. And in literature, usually, at least the new works, they use demonstrations or natural language for giving this kind of instructions to the agent. But the main issue here is these are ambiguous instruction modalities, right? We can debate about what a natural language sentence really mean. So there is that ambiguity, and I think this might be a fundamental challenge for building trustworthy systems. So then we believe formal models are trustworthy. So how can we incorporate them in this pipeline? So I'll just draw a picture here, and then we can talk about the details of this. So I think it would be very nice if we could just take these instructions in natural language and then somehow translate them to a formal model. And I know this is not an easy thing to do, but just let's assume it's possible to do. But if we could if we could do something like that, then we could pass this formal model to the agent as well. But then, of course, and then once we do something like this, I think this kind of breaks the pipeline in the sense that by solving the ambiguity, by basically distilling this ambiguous instruction into a precise representation, we are kind of splitting this pipeline, because let's say the user gives an instruction, and then we have the automaton for this, then we can actually runtime monitor the downstream task, maybe. Yeah.
So is it just a structured representation of the prompt, or is actually, it's pretty common in LLMs now to have a prompt, then have a planning LLM that says, okay, give me a plan, and then there is a separate execution, or is it just a structured representation of the prompt? That's it.
I mean, it can be both of them. So right now, I'm not saying anything specific about how you would get this DFA. And then there could be different ways to get this DFA.
No, but is this DFA just a representation of the prompt, or like a plan to do that task?
A plan. It's a plan, basically. So what you need to do to accomplish the task. And I think plan is an important word here, and we will talk about this. And then if I had this automaton, and let's say there was some bad consequences of this task, and then I can go ahead and check, okay, what was the precise thing that the system understood? So what was our formal model? And then we can go ahead and see and check the behavior with respect to this formal model, and then say, okay, maybe policy did something wrong. There was nothing wrong with the plan, but the policy made some mistakes. Or maybe policy was correct, but the plan itself was problematic. And then we can now blame the left-hand side of this picture. But the question is, how can we efficiently do this left-hand side? How can we even translate these to formal models? And then on the right-hand side, we have this other question where how do we actually communicate this formal model to the downstream system? And in today's talk, we'll just focus on the right-hand side of this picture. And there are some other works to accomplish the left-hand side. But I think to get some interesting results, maybe working on this right-hand side will give us tools to tackle the left-hand side, the inverse problem too. So I'll first start with goal-conditioned reinforcement learning, just to set the stage. And then I'll talk about automata as a goal representation. And I'll give the precise definition of automata-conditioned reinforcement learning problem and its pack learnability. And then we'll talk about learning provably correct automata embeddings and how do we even think about provable correctness in this setting. And then I'll conclude. So goal-conditioned RL, it's basically a framework to think about problems like this. So a user gives a goal at runtime, let's call it GT, and then the agent interacts with the environment by conditioning on this goal, and then gets observed its next state. And our goal is to basically learn a policy pi, maximizing this expected discounted reward. And the catch here is the reward function now also depends on the current goal. So we want to use deterministic finite automaton as a goal representation. And here I try to give a simple formal model for this example task. We want to do this because, as I argued before, formal models are unambiguous. Moreover, DFAs, they capture minimal additional memory necessary to plan. And we'll talk about the fact that minimized DFAs are canonical task representations, and we'll use this fact too. DFAs are more expressive than linear temporal logic. For example, the parity language cannot be expressed in LTL because LTL can only express star-free languages. And also, DFAs are compositional objects. They are closed under Boolean operations, and they have parallel and sequential compositions. We can define these things on them. So this sounds good, but of course, there are some challenges involved on this path. First and foremost is the reward sparsity. I think anyone who worked on LTL and reinforcement learning know that this is a problem. And the reason is DFAs give sparse feedback. They just say, did you reach the accepting state or not? So most traces get 0 reward. Most traces don't get any positive or negative reward. And then you can say, okay, what if I did planning myself and then just rewarded based on, did you reach this next symbol or not? Is that enough? Because that's a denser reward signal than the first one. It turns out that it's not enough because hierarchical planning in this domain is suboptimal. So if you were to just plan over this DFA and then instruct what the next symbol you're supposed to see, just give the next symbol to the agent, that's not the same thing as giving the entire task. Because saying go to orange and then go to green is not the same thing as saying go to orange, full stop, wait until the agent goes to the orange, and then say go to green. And here you see an example where the agent, if you give the second one, the agent first goes to the closest orange one because it doesn't know that it's supposed to go to a green square afterwards. So this kind of hierarchical planning doesn't give us the optimal behavior we want. So the policy must take the entire DFA into account. Somehow it needs to know the entire DFA. But then what is the prior distribution of DFAs to train on? And there's that question. Well, that's another challenge. It turns out DFAs form a countably infinite concept class. So any distribution you define is necessarily biased. So then we'll think about how can we achieve generalization here? What is the kind of bias that could help us? And the last challenge is there's this exponential size growth issue. Specifically, I said these are compositional objects, so we want to efficiently compose them, but the conjunction of, let's say, as an example, conjunction of k DFAs, each with n states, has n to the k many states. So if you just give me large DFAs and wanted me to take their conjunction, even just symbolically computing that takes a lot of time. So how do we handle this so that we can actually use the compositionality of these objects? So we have three main challenges: no prior distribution, reward sparsity and suboptimality, and exponential size growth. For the first one, I'll just give an intuition now. We'll utilize the graph structure of DFAs, and we'll observe that most tasks resemble a sequence of reach-avoid problems. And then we'll try to use this intuition to define a prior distribution over DFAs to train on. And for the other two, we'll learn embeddings and avoid symbolic computation as much as possible. Okay, so the full picture looks like this. So the user gives, or we sample a DFA from a distribution that we don't know yet. And then we'll pass this through an encoder. We'll pass this to an encoder and then get a latent representation, get a vector representation for this DFA. And then we'll pass this representation to our downstream policy. Our downstream policy will interact with the environment conditioning on the goal, get the next state, and then we assume a labeling function associating MDP states to symbols in your alphabet. So this red and green squares that you see. So this is the full picture, but to realize this, we need a roadmap. So our plan is we'll first talk about what is the DFA distribution, what is this prior distribution we assume on DFAs, and hopefully it's going to help us generalize. Next, a DFA conditioned RL problem, we'll formally state that and see that it is actually pack learnable. Then we'll think about how to map DFAs to vector representation. So what is this encoder actually? Next, we'll talk about our pre-training procedure. So how to learn provably correct DFA embeddings. And then how to efficiently compose these DFAs, addressing our last challenge. And finally, does DFA conditioned RL actually generalize? Because that's what we want. So let's start from the first one. Just quickly, I'll give the formalism. So we have a DFA. I'll usually just use the graphical representation. And it has a set of final state. We just assume they can be partitioned into accepting and rejecting final states. And then our semantics are three-valued semantics. So you either accept, reject, or neither. And then we did this notion of similarity between DFAs because just like we said a couple of minutes ago, we are going to treat these DFAs as plans, and we want to compare different kinds of plans. So this notion of bisimilarity is going to help us. So informally, two DFAs are called bisimilar if they are behaviorally indistinguishable. And the intuition in this example is same string leads to the same behavior. So these two DFAs are bisimilar. And just building on top of this intuition, DFAs can be minimized into a canonical representation using a classical algorithm. And again, the intuition is, for example, for these strings, no suffix changes what you see in the feature. So you can just merge Q and Q prime and get the DFA on the right. And DFA on the right is your canonical plan representation, your task representation. And I'll be specifically in the rest of the talk. This is my assumption. I assume that we work on these plan DFAs. And a plan DFA is defined as follows. No suffix can turn an accepted string into a not accepted one. So specifically, if you give me this DFA, so if any state Q is in the accept set, then any outgoing transition goes to an accept state. And same for the reject one too. And then obviously, if you minimize such DFAs, you'll just have one sync accept state and then one sync reject state. Okay, so we set all these tools. So I think I did the setup. So just coming back to our question now, what is this task distribution that we want? So for this, let's look at some distributions from the literature. And we'll look at them and ask, how can we generalize to these and then some other, probably some other task classes that we don't know yet. So I'll give their DFA and their finite LTL representation. So one task that is used are these, we call them reach tasks, sometimes called partially ordered tasks. So you just give an ordering over your symbols, and it can be represented with an eventually operator in LTL. You can have reach avoid tasks where you're trying to reach a symbol while avoiding something else. And they can be written using an until operator. And then we define this kind of variation of reach avoid, like reach avoid with redemption. So you have this other symbol that takes you back to the other state. And they can be also represented in LTLF. Or you can define a sub class of reach avoid redemption called parity, where this is basically saying you need to see orange an even number of times. And this cannot be written in LTL. I'll just leave it as an exercise. But yeah, that's the case. So we want to generalize. These are the kind of tasks that we see, and some of them we came up with. We want to generalize these and potentially some more. So what is the kind of bias that can help us generalize here? And here I just want to remind you that we want to define a DFA distribution that will help us generalize for the downstream task, because we don't know what task distribution we'll see. So let's take a look at the DFA. This DFA, it's not a reach DFA, it's not a reach avoid DFA. It looks like a reach DFA, but not exactly. So it kind of resembles all of them. And actually here we can observe that any path in a DFA, once you fix that path, it can be formulated as a sequence of reach avoid problems. So if you fix this path, actually what this path is saying from the first state, reach orange, and in the second one, it is saying reach green while avoiding red, because red takes me away from my path. So can we now turn this intuition into a DFA distribution, basically a random DFA space? So we define this reach avoid derived DFA distribution. It has 4 steps. So first, you sample a sequence of reach avoid problems, and it looks like this. So at the beginning, your first problem is go to orange, avoid red, and so on. And then for each non-reach avoid symbol, so other symbols you have, add a stuttering transition with a certain probability, or make it reach or avoid symbol with equal probability. So we are just trying to mess with the structure of this DFA, just add some random connections, and then just mutate them times, just get your transition matrix, randomly toggle some of the entries, and then minimize. And of course, while doing that, make sure that at the end, you still get a planned DFA. So through these steps, we define this rat DFA distribution. And in the experiment results later, I'll try to convince you that this actually works, because this distribution kind of captures the reach distribution, reach avoid derived, reach avoid distribution, and all these other DFA distributions for planned DFAs. So this will be our training distribution. So we know it now. Okay, so the next question, what is the DFA conditioned RL problem? To do so, we'll need to define this DFA space object. So these DFAs that I just defined, is rat DFAs, they form a DFA space. And here's what I mean by that. Let's take this rat DFA, and let's imagine this as a state itself. And then we read orange and then minimize it, and then we get a new DFA now. It's a smaller DFA. It's a sub DFA of the previous one. And then from that one, if I read red and then minimize, I'll get the trivially rejecting DFA. And similar for the green one, I'll get the trivially accepting DFA. So building on this intuition, basically we'll say a set of DFAs over some shared alphabet and with at most n states, they form a DFA space if I have these trivially accepting and rejecting DFAs, the sinks of the space in the set. And if taking any path from a DFA and then minimizing the resulting DFA gives me a DFA from the set. So all these DFAs that I drove here, they should all be inside the set. So these DFA spaces, they almost trivially induce this deterministic MDPs.
So your DFAs can have cycles, right?
They can have cycles in there, but I still have the condition that you cannot turn an accepting string into a rejecting one. Sorry, you cannot change it. So here basically what I'm saying is we are considering safety and co-safety properties that can be checked with a finite trace.
Yeah. So when you say take any path in a DFA, this is finite length path. I mean, this is a path.
Yeah, it's a finite
bounded
length
path.
Exactly. So that's basically saying if I just took this path, so like orange-red path on this DFA, if I take that path and then minimize, it gives me this trivially rejecting DFA. And this needs to be inside the set. So basically what I'm saying is any random walk on your DFA, the resulting DFA you get from that random walk needs to be inside this set. So no matter what I do to my DFAs in this set, I'm still inside the set.
Yeah.
Sorry?
I mean, is it just changing the initial state? Because if I have cycles.
Yeah, it's changed exactly just that. So I'm just updating the initial state and minimize that DFA. So we can define a deterministic MDP on top of this object easily, where now your states are DFAs from this DFA space. So in this MDP, the states are DFAs, and your actions are symbols in your alphabet. And your transition functions are basically these. Just take the transition and then minimize. And your reward function, if you're here, you get a plus reward. If you're here, you get a -1 reward, otherwise 0. So now I can use this deterministic MDP to define a DFA conditioned MDP, where I basically take the cascade composition. You give me an MDP and a DFA space and a labeling function associating states to symbols. Then I take the cascade composition of these two and then use L to map states to symbols. And basically, given an action, we first take a transition in the underlying MDP, get the next state, label that, and use that label to take a transition in the DFA space. And then you reward based on whether or not you're in the accepting or rejecting sinks. And as you can see, the next slide almost, if you're still with me, next slide is almost trivial now. And just notice cascade composition of two MDPs is an MDP. So what we're going to do is just the DFA conditioned RL problem. So now we learn a policy that conditions on DFAs in my space and then predicts an action distribution over them. And the DFA conditioned RL problem is now over my DFA conditioned MDP, and I want to find the optimal policy. So it is pack learnable. So the way we think about pack learnability in this context is as follows. An algorithm is called probably approximately correct in MDPs if it finds a near optimal policy. This is what I mean by near optimal. So you're epsilon close with high probability, with probability 1 minus p. In any MDP, after a number of interactions, polynomial in the key parameters of the algorithm. So this is the framework, the way in which we think about pack learnability in this context. And as I said, the cascade composition of two MDPs is an MDP. So if you have an algorithm that is pack MDP, it will also be pack MDP in any DFA conditioned MDP. You just need to consider the states in your DFA space too. So nothing surprising here. And these pack learnability results, they were given for single tasks. So using DFAs in single task settings, those results were given previously. We are just extending it to the the automata condition setting. And through our construction, it's very easy to do. Okay, so it's pack learnable, everything is good. What is stopping us? Yep.
Need a discount factor here, right? In order for this to be pack learnable?
Yeah, I didn't write that, it's here.
So you need a discount factor here in order to be pack learnable.
Yeah, gamma is the discount factor.
So,
but actually, since these are only safety and co-safety DFAs, so they only all accept finite traces. So you don't really need. So I'm not working on a Buki automaton. You don't need a discount factor to get the packed learnability result. But it's still inside it. I just like didn't
Yeah, so why do
exclusively
you
say gamma.
maybe my question then simply is why would you discount if you're in the co-safe setting?
So why do I need this gamma?
Yeah, why do you want to discount exactly?
You don't have to discount if you're in the co-safe setting. Yeah, that's true. You don't have to.
Thanks.
And then, okay, what's stopping us? It's packed learnable. The problem is you cannot just give a DFA to a policy directly. We need an encoding. And one way to do this, of course, you can map your DFAs to integers. It's countably infinite. So you can just give an ID to each DFA, but that requires me to enumerate my DFA space, which I don't want to do. You can jointly learn an encoder, but this is going to make the reward sparsed even worse. So we need to be smarter than this. So let's do that next. But I need one more thing to set up here. How do I map DFAs to vectors? So we'll use graph neural networks to do so. So given a DFA, we'll construct this featureization of the DFA. So we'll introduce new nodes for each symbol, flip edges, and add soft loops. The reason why we do this is graph neural networks works as they basically, each node send messages to the others, to their neighbors at each step. And we specifically use a graph attention network, but the idea is you basically do this permutation invariant aggregation over the messages at each node. And then after the last step, the feature vector of the initial state is your plan now. And we do this, so if you, in your featureized DFA, if you have n nodes, we do this message passing step n times. The idea is we want to get messages from even the furthest away states too. So we want this initial node to get messages from everyone. Okay, I'm not going to talk about the GNNs more, because I think this is more interesting. So, okay, how do I learn provably correct DFA embeddings? I now know how to map DFAs to vectors, but how should I train this to get what I want? So one way to think about this problem is, so far what I set up, all the formulation was for conditioning on a DFA. That was the theoretical idealized version of the problem, and we show that it's packed learnable. And now we want to condition on DFA embedding. So we want to pass these through this phi, and then we want our agent to condition on this. And the question we'll ask this, are these equivalent? Are these equivalent problems? So formally, given a DFA space, we want to learn an encoder phi such that in any underlying MDP M, solving the DFA conditioned MDP, the cascade composition with a policy pi z, so this part, is equivalent to solving it with a DFA conditioned policy pi, conditioning on the actual DFAs themselves. So if these are equivalent, I can just pass them through my phi and everything would be okay. Any guarantee that I have for left-hand side would directly translate to the right-hand side. So what this means is encoder must represent each task uniquely. So the encoder phi must guarantee that a DFA pair, A and A prime from the space, they have the same representation if and only if they are bisimilar DFAs. Why? Because bisimilar DFAs they represent the same task. They are just different structures for the same task. So we don't need to distinguish between bisimilar DFAs. Okay, so this is the intuition. I need a little bit of background here. So we'll think about bisimulation relations and metrics over MDP states. So previously I gave the bisimilarity definition over DFAs. Now this is something slightly different, but we'll see that they're equivalent. So given an MDP, two states are bisimilar if they behave identically in terms of their rewards and transitions. Let's just keep it informal for a second, and then we can immediately see that this definition of bisimilarity is equivalent to DFA bisimulation with respect to the induced MDP. So let's take this DFA, and then let's take a bisimilar DFA. These two are bisimilar. I'm not giving notation for the initial state, but it can be any of them. It's just like think about it as like symmetric. So if I take the orange from the first one in my induced MDP in my DFA space, I'll get this DFA, and all the other symbols I mean, one of them takes me, red takes me here, but that's again a bisimilar DFA anyway, so I'm not showing that here. And here, if you read orange from the bottom one, you still get to the same DFA, and from the green, it's the same thing. So for these DFAs in the DFA space, they are equivalent in terms of their rewards and state transitions, and they are indeed bisimilar DFAs too. So these are actually equivalent definitions. So then bisimulation metric is a relaxation of this notion of a bisimulation relation. So now we have a pseudo metric, and it's called a bisimulation metric. If between two MDP states, it is saying that the distance is 0, then this means they are bisimilar. So if the pseudo metric satisfies this, the induced relation is a bisimulation relation, then it's called a bisimulation metric. Okay. So given all this, the approach is as follows. We want to measure how bisimilar two DFAs are. So let's take these two. They resemble one another, but they are not bisimilar, that's for sure. So the idea is take the phi that we are trying to learn and define your bisimulation metric as the L2 norm of these embeddings that you get from phi. And if we train it to be a bisimulation metric over the DFA space, it will be basically learning a transition, learning a table like this, where basically each DFA is bisimilar to itself, and then you have the same entries on the reverse diagonal. And because if I can train this, if these are bisimulation metric, then it will say 0 if and only if I have bisimilar DFAs. But because I use the L2 norm, I also get this. So basically, the property I want is here. If I could get a bisimulation metric, my encoder phi would have the property that I want. So how do we compute these bisimulation metrics? So given a deterministic MDP, we'll define two operators. The first one is the operator that learns the bisimulation metric. Other one is this argmax policy. And you can just write them down in a single equation too, but I'm writing them differently. And this is actually a result that was shown that these operators have unique fixed points. And the unique fixed point of this one with the optimal policy is the bisimulation metric that we're looking for. And the idea is here, what's actually happening in these equations is the following. I give you two DFAs. So these S's here now are DFAs for us. And then the policy, the argmax policy, computes, it gives us an evidence that these two DFAs are not bisimilar, right? Because it is trying to maximize this reward difference. So here it will say green. And then basically we use that action to then compute this table for our bisimulation metric. And basically these results that these unique fixed points exist and so on, these results were first given by Ferns et al. In these two citations here. And then that result was later extended to deterministic MDPs by Pablo Castro. And then later Amy Zhang gave a proof that you can jointly learn a policy while learning this bisimulation metric. So we are boiling this down. So in practice, we'll sample two DFAs with our phi, we'll map them to vector representations. We'll compute the bisimulation metric, which is the L2 norm of the embeddings. And then we'll use these latent representations for our policy for our argmax policy. And then we'll use that action to take a translation. So it's kind of as if we are playing a bisimulation game here. And then the way we learn it is, this is our objective. The first one is the clip objective from PPO. The details are not important. It's not guaranteed to find the optimal, so the global optima, but it usually does so. So the first part, the clip objective, is for the argmax policy. And then the other one, the value objective, learns the bisimulation metric. And basically we have our usual estimate and our one-step look ahead that we're trying to learn. So once we do this, we will call our trained embeddings RAD embeddings, reach over derived RAD embeddings. Okay, so some results. RAD embeddings uniquely represent distinct tasks. So The optimal encoder 5 star gives me what I'm looking for because this will be a bisimulation metric and L2 norm is equal to 0 if and only if they have the same representation, and that happens if and only if they are bisimilar. So when we train this, the objectives are now shown as loss here. We quickly learn the bisimulation metric over DFAs. And here I generated some reach avoid derived, reach, and reach avoid DFAs. So these are they have at most 10 states. And this is what we trained on. So we trained on at most 10 states. And here these DFAs, they have at least 10, but at most 20 states. So we never saw DFAs this large during training. And when we check it, you actually, maybe you can see it, the diagonal of the heat map is 0. And we even get 100% empirical correctness for out of distribution DFAs as well. And these embeddings actually enable optimal multitask policy learning. Just a sanity check using our example before, when we train a controller, we quickly learn the optimal behavior, essentially because RAD embeddings make the product state Markovian, because all the information you need is in your product state now. RAD embeddings overcome reward sparsity. So here, the letter world is a discrete domain. Zones is a continuous domain. And we trained with graph attention networks. So no pre-training means we are jointly learning the encoder too. No pre-training. Pre-training means we pre-trained, but there is still gradient flow to the encoder. And frozen means no gradients to the encoder. And RGCN is just a different a GNN architecture. And essentially what we see is the freezing the encoder gives the best performance. This solid green line is for gateway to pre-training and frozen. So once you learn them, you don't need to keep learning. And essentially what we see is here, the decoupling to the representation learning and control learning help with reward sparsity. And also correctness indeed matters. So what we did here is the blue one is so we trained a downstream policy with frozen encoder, with a frozen encoder. But for the blue line, the encoder was trained with the bisimulation metric idea that I just shared. This is DFA solving. I'm not going to get into the details of that. It's just a different pre-training procedure, but it doesn't have the correctness guarantee. And the other one is just jointly learning the encoder too. And what we see is if you don't have the correctness guarantee, it's harder to learn the red line. And the correctness further helps with the reward sparsity because it's easier to learn now. Okay, so the last one, exponential size growth. How do I efficiently compose DFAs? Idea is pretty simple. Just one slide is enough. Just don't compute it. If it's hard to compute, just don't do it. Instead, introduce the special node. That's the conjunction node, and connect all the DFAs you have in your conjunction to this node and represent your task this way. And then you can define a C-RAD distribution, a compositional RAD distribution on top of this, where you just sample another value for the composition. And here, notice that any of the arguments I gave, they do not assume anything about the structure of this. The way the symbolic representation of the task is not important. So all the guarantees directly translate to here too. This is just a different symbolic representation for the same task. Okay, so we got that too. Let's look at some experiment results. Does DFA conditional RL generalize? So they do indeed. So we generated a bunch of samples. So here we generate, so the syntax is as follows. You'll see, you don't need to read all of them, but basically C-RAD ABC means we sample a N from uniform CD distribution, and then our DFAs are compositional reach avoid DFAs, each with length sample from this AB part. And here you see, so parity, so P means parity, R means reach, and so on. The details are not important, but what we want to see here, the frozen one, the green bar, kind of dominates others across the board. So freezing And because once you learn your good representations, you don't need to keep training. It just makes things worse. Just freeze it, and it's going to generalize. So this is the message here. Okay, so in conclusion, we handled the compositional of the problem too. So we combine our DFAs in these AND structures, use our encoder to map them to vector representations, and then use that for the downstream control. And the TLDR is red embeddings enable optimal GCRL for temporal tasks. And I want to leave you with two questions. This labeling function is such a big assumption, associating states to symbols in the alphabet. So what can we do about this? And also the other side of the problem. Now that we have this nice embedding space that we have control over, that we have this provable correctness over, can we translate natural language instructions or demonstrations or other modalities to this space, and then basically use this for the downstream task? So I'll just leave with these questions. Thank you very much.
All right. Yeah. So, are there any questions? Okay. Coming up with discussion.
Thanks for the very nice talk. There's the notion of epsilon bisimulation, which basically says that you are bisimilar up to some epsilon. I was wondering whether you also can get some results in your embedding that you can say epsilon bisimilar in the piece.
You
will
mean
be
kind of
close.
like based on their like positions in the space, can we? That's interesting. We didn't think about that, but yeah, that's I think worth investigation. We haven't thought about that though. Yeah.
Thanks.
Anyone else? Okay. One more from Sebastian.
I can keep on doing this. Well, final question. You have this and here. Do you do the same thing for ors? Like if you want to.
Yeah, you can, because honestly, the trick is, so you don't compute things symbolically. You give it to the learner, and it's supposed to figure out that this node, and like we have like in our encoding, this is like a special node and so on, and the learner figures out that's basically an operator node. So you can probably just put an or node there, and then even have like a CNF structure and so on, both and then ors, and then do the whole thing. We didn't do it because it felt like trivial. We can just do it if you had that special node. But definitely that's something we mentioned in the paper too.
So I'll have one for Beyazit since I so many of the results that you showed for the theory, you know, they were, you started off with this motivation that we have a countably infinite set. But there's in some sense a problem here where we're trying to fit a countably infinite set into a finite box, and that box itself is uncountably infinite. But you know, with floating point numbers, this is a you know, there's only so many floats that we can use, and so necessarily, you know, when you do a real approximation of this, you're going to get a pigeonhole principle, and two DFAs are going to map to the same cell. And so, do you have any thoughts on that?
Yeah, I mean, all the results I give like are with respect to a finite set of DFAs that form a DFA space, but definitely as you go larger, and then I think something like that will require us to think about the graph neural network and the way it summarizes the DFAs. But maybe if it's not enough to fit there, it might still be okay, because basically maybe that level of information is enough for the DFA you have at hand. Yeah, so I think that's something that we're going to investigate.
Right. Well, thank you, Beyazit, and pause. Yeah, actually, there's a property that happens that